Chapter 9. In this chapter, we will cover the ratios of reactions, conversion, stoichiometry, limiting reactants, and limiting reactant calculations. The meaning of coefficient is balanced chemical reactions show the ratios in which particles, that could be molecules, formula units, or ions, are used up and form. For example, the burning of heptane can be represented as shown it here. This is chemical equation. So we have heptane, one molecule heptane burns in 11 oxygen molecules and forms 7 carbon dioxide molecules and 8 water molecules. Now, if we double the number of heptane, what happens? So basically, we would expect that 22 oxygen molecules will be consumed, and 14 carbon dioxide molecules will be formed, and 16 water molecules. So it is double. We double all the numbers when we double the number of heptane. So as we see here, the number may change, the amount may change, but the ratio is still the same. For example, here it was 1 to 1 heptane per 11 oxygen, 1 heptane per 7 carbon dioxide, and 1 heptane will form 8 water molecules. And here it is 2 to 22 equals to still it is 1 to 11 ratio. So the ratio doesn't change when we change the coefficients. It's always the ratio of each chemical to each other would be constant. So in a balance equation, coefficients are calculated based on the counts of the atoms. So because atoms are not divisible, you can't have like 2.5 oxygen atoms or 5.6 many hydrogen atoms. So the number of atoms are even, so they have to be whole numbers. That's why the coefficients cannot be they have to be whole numbers. They cannot be fractions. So when we react hydrogens and oxygen, so what we have here, after we balance it, you have 2 hydrogen molecules, and react with 1. When we don't see any number, it is 1. So 1 oxygen molecule, and so they form 2 water molecules. So we can read that. We can say that 2 molecules of hydrogen used up equals exactly 1 molecule of oxygen used up. So it is 2 to 1 ratio. 2 hydrogen molecules per 1 oxygen molecule. That's the ratio, the smallest ratio. Or we can say 2 molecules of hydrogen consumed equals exactly 2 molecules of water formed. So that means when we consume 2 hydrogen molecules, it will form exactly 2 water molecules. If 1 molecule of oxygen reacts, exactly 2 molecules of water must form. That is the ratio again. So when reading an equation, the units attached to the coefficients can be read as exact count of particles or exact moles of particles. So for this one, we can write 2 mole hydrogen used up equals to 1 mole oxygen used up. So that is kind of equality. We can use those coefficients as equalities, and then we can use those as conversion factors to solve problems. Or we can say 2 mole hydrogen molecule used up equals to 2 mole water formed. 1 mole oxygen used up equals to 2 moles of water formed, and so on. So these exact equalities can be used as conversions, as I said earlier, to solve calculations for these reactions. For example, here we got carbon sulfide reacts with oxygen, forms carbon dioxide and sulfur dioxide. Now the question is, if 4 molecules of carbon sulfide react, how many molecules of oxygen must be used up? So we're dealing with these two molecules, two compounds. But to solve this kind of problems, we have to balance the equation first. And to balance it, so as we go back here, you see here we got 2 sulfurs, here it is 1, so we can put 2 here, and so the oxygen becomes 4, 2 here, that's 6, so we put 3 here. That will balance the equation here. So now after we balance the equation, we can go ahead and do the calculation. Now, according to the equation here, we start with 5 moles. That is our starting point. 5 molecules, not moles, the molecules of carbon sulfide, and that is our starting point times. So according to the balanced equation, we got one carbon sulfide reacts with 3 oxygen molecules. So it's one molecule, carbon sulfide molecule reacts with 3 oxygen molecules, and so we cancel out the mole carbon sulfide, so they cancel out, and what is left is mole oxygen. And when you would do that, you come up with 15 moles of oxygen. And it makes sense because according to the balanced equation, one molecule's carbon sulfide, 1, so if there is no number, that is 1. So one molecule requires 3 oxygen molecules. Now, if you increase the number of molecules of carbon sulfide 5 times, then you will have to increase the number of oxygen 5 times. So it will be 5 times 3. That is what we're doing here. 5 times 3, that's 15 oxygen molecules. That's how we solve the problem. So again, multiplying this, increasing that 5 times. So this is 3. You have to increase that 5 times, so that's 15. And so that's what happens. So basically increasing that, so you just have to multiply all coefficients by 5, and that is what you come here. So from here to here, of course, you can use the equality starting point and equalities here. Those coefficients, those are the equalities. You can solve the problem. The other question, related question, is if 3 molecules of CS2 react, how many molecules of SO2 must form? Now here we compare those 2 chemicals. Again, CS2 is the reactant on the left side of the arrow, and the SO2, sulfur dioxide, is the product. So you start with the 3 molecules of that is what we start with, 3 molecules of CS2, and according to the balance equation, 1 CS2 can form or produce 2 S2 molecules. And so our goal here is to cancel out the CS2s and come up with SO2s. You do the calculation, you come with 6 molecules of SO2. So again, it makes sense because we're basically increasing the number of CS2s 3 times, and the number of product, the SO2, will increase 3 times. So basically you're just multiplying this reaction by 3, and those are the coefficients. Again, the number of the coefficient might change, but the ratio is always the same. So for example, for CS2 to oxygen, it is 1 to 3. CS2 to SO2, it is 1 to 2. Still, it is 1 to 2. If you take the simplest ratio, that will be 1 to 2 ratio here. So for this chemical reaction is balanced. Ammonia reacts with oxygen to form nitrogen monoxide and water here. How many moles of ammonia are used up to form 8.4 moles of oxygen? Water. Again, here we're comparing this ammonia and water. So you see the ratio is 4 to 6, and our starting point is 8.4, 8.4, and then we use the coefficient here, ammonia and water, so 4. Now the goal is to cancel out water, so we put 6 in denominator here, this 6 here, and so that means 6 moles of water are produced from 4 moles of ammonia. You cancel out the waters, and your answer will be mole ammonia. That is what we're looking for. So that is how many moles of ammonia. So moles of ammonia is for 5.6. So you multiply 8.4 by 4, divide by 6, you come up with 5.6 moles of ammonia has to be consumed to form 8.4 moles of water. So the second part of the question is how many moles of oxygen are used up to form 6.2 moles of NO. Now this time we're comparing those two chemicals. Again, oxygen is the reactant, NO is the product. And our starting point is 6.2 NO. So that's what we start with. And then we use the bridge, the relationship between those two. So the NO has to be in denominator, and the coefficient of NO is 4. So this is what we have here. So, and 5, to form 5 moles or 5 molecules, well, in this case it is mole. So 4 mole NO is formed from 5 moles of oxygen. So you cancel out the NOs, nitrogen monoxide, and mole nitrogen monoxide, of course. So, and what is left is mole oxygen. So you multiply these two numbers, 6.2 times 5 divided by 4, so you come up with 7.8 moles oxygen. Okay. Another question here. How many moles of iron trioxide are consumed in reacting with 4.880 mole carbon? So this is carbon, and so here carbon and iron trioxide. But it says here that this reaction is not balanced. We have to balance it first to solve these problems. Without balancing the equation, you come up with wrong numbers. So the first thing we do is to balance the equation. We have to balance the equation first. And of course, you can see that Fe2, that's in iron trioxide. So in here, the iron is 3 plus charge, so that's why we call it iron Roman numeral 3 oxide. And so this 2, if we put that 2 in front of this iron, we balance the iron on both sides. And the oxygen here is 3. If we put that 3 in front of carbon monoxide, so we balance the oxygen, and so carbon becomes 3, so we have to put 3 there. Now it is balanced equation. Then we can go ahead and solve the problem. So our starting point is 4.80 moles carbon, and again here we're comparing carbon and iron trioxide. So how many moles of iron trioxide are consumed in reacting with 4.8 moles? So that is what we have, 4.80 moles of carbon. And according to the reaction, 3 moles of carbon can react with 1 mole iron trioxide. So you cancel out the mole carbons, and what is left is mole iron 3 oxide. So you just do the math, 4.80 times 1 divided by 3, and that is 1.60 moles of iron 3 oxide. And again, our starting point 4.80 has 3 significant figures, and our answer here has to have 3 sig figs. So that is what we have here, 1.60 here. That number has 3 significant figures. The second part of this question is to form 3.6 moles of iron here, how many moles of carbon are needed? So again, according to the balanced equation, to form 2 moles of iron, 3 moles of carbon is required. So that is what we have. That's the equality. That means like 3 carbon equals 2 Fe, right? So our starting point is 3.6 moles iron, and so the equality here, 3 moles of course, iron has to be denominator so that we can cancel out. So 2 moles, according to the balance, 2 moles iron are formed from 3 moles of carbon. So you cancel out, and then what you do, 3.6 times 3 divided by 2, you come up with 5.4 moles carbon are required to form 3.6 moles of iron. So this is another question. Ammonia reacts with oxygen here, and see, it is already balanced, so we can go ahead and solve the problem. Again, our starting point is 14.0 moles of ammonia. So ammonia and oxygen here, so those two, and so we have to look at those coefficients, right? 4 moles of ammonia requires 3 moles of oxygen. And so we start with 14.0 moles of ammonia, and so the denominator has to be ammonia here, 4 moles, that's 4, that is 4, and that is 3, so 3 moles of, so once they cancel out, the moles of ammonia cancel out, and you multiply that number by 3 divided by 4, you come up with 10.5 moles of oxygen are required to burn 14.0 moles of ammonia. And again, the initial has 3 significant figures, and your answer has to have 3 sig figs. The second part of this question, how many moles of oxygen must be used up if 20.0 moles of nitrogen form? So again, here we compare those two. Again, our starting point is 20.0 moles of nitrogen, and then the ratio here is 3 mole oxygen equals to 2 mole nitrogen. So you could use that equation, equality, and we can convert it to conversion factor as we see it here. And then the mole nitrogen will cancel out, and the target is mole oxygen. So you multiply 20 by 3 divided by 2, or you can simplify it. So 20 by 2, that's 10. 10 times 3, that's 30.0. So it has to have 3 sig figs. 3 sig figs. So you can have 30.0 moles of oxygen. So you have to consume 30 moles of oxygen to generate 20 moles of nitrogen. So again, the conversion stoichiometry is a Greek word. It means measuring fundamental quantities. So we're just using the coefficient we can come up with. We can calculate like similar to calculations that we've done so far. So our steps in this type of stoichiometry are as follows. If needed, convert the units of the given amount to moles. So because the coefficients, they stand for moles, not for grams, the coefficients that we see in a chemical reaction. Use the bridge ratio This is a relationship between the chemicals, among the chemicals supplied by the balance equation to convert from the given moles to the wanted moles, and then convert to other wanted units if needed. We'll see examples. So the burning hydrogen gas in air forms steam by the following unbalanced equation. Again, that is the so here there's a question like 30 if 32.0 grams of oxygen is used up in the reaction, how many grams of water form? Okay, so that's oxygen here, 32. If 32 is formed, so how many if 32 grams of oxygen are used up, here we assume that we got enough hydrogen, and so how much water can we generate using 32 grams of oxygen? Again, the wanted is gram water. That is what we're looking for. How many grams water? So that is our wanted, and the data that is given is 30. That's the 32 grams of oxygen, which is here. We put it there. And the other thing is the molar mass of water. So one mole water equals to 18.0 grams water. And the other one is the those are the given numbers that we have to solve this problem. And one mole oxygen is 32 grams. So if you check the periodic table, one oxygen atom is 15.999. So um, we take it as 16 for sake of discussion. And so we have to, again, as we said earlier, we have to balance the equation first, and that is now balanced when you have 2 moles of hydrogen, 1 mole of oxygen generates 2 moles of water. And then the bridge here, the bridge ratio here is the relationship between water and oxygen. So when you look at the balance equation here, 2 moles of water can be generated from 1 mole oxygen here. So those are that. So you can write it as equality, and then we can use that equality as our conversion factor. So again, here the starting point is 32 grams oxygen, and then we use the conversion factor, the relationship between oxygen and so that we use the conversion factor, the molar mass 32 grams. 32 grams oxygen is 1 mole oxygen. So now gram oxygen is gone. So what we have here is mole oxygen, but we're not looking for mole oxygen. We're looking for grams of water. That is our starting point. So according to the reaction, 1 mole oxygen can generate 2 moles here, 2 moles of water. And again, we're not there yet. So mole oxygen is gone. Now we got mole water so far. And we need to do one more step to convert mole water to grams. So to do that, we have to use the molar mass of water, which is 1 mole is 18 grams. And so your final unit now is gram water, and that is what we're looking for here. And the rest is just the math, 32.0 times 1 times 2 times 18, and then whatever number you get divided by 32, and you come up with 36.0 gram water. And of course, you have this 32 here, 32 here, they can cancel out. I mean, you can simplify it. And what is left here is 2 times 18, that's 36 grams. Okay, so for the unbalanced equation, sodium burns in oxygen to form sodium oxide. And the question here is how many grams of sodium oxide the molar mass of sodium oxide is provided in parentheses here, can be produced from 2.3 grams of sodium, and molar mass is of sodium is given in parentheses here. And so basically we can use those numbers here, the molar masses, as conversion factor to solve the problem here. Again, the first thing we do, we have to balance the equation. Remember here, we got two sodiums here. You can put 2 in front of that, but well, the oxygen here, so you can start with that. You can put that in front of that, and so you balance the oxygen. You got 2 on the left, 2 on the right, and when you do that, 2 times 2, that's 4. So you have to put 4 in front of sodium to balance the sodium atoms. And our starting point is 22.3 grams of sodium, and then according to we have so here the goal is how many grams of sodium oxide can be produced from the sodium. So that is, we're comparing those two chemicals. Okay, so 2.3 grams of sodium, and again, because the coefficient is moles, we have to convert the grams of sodium to moles of sodium first. That is what we're doing here. And using the molar mass of sodium, so again, this is the starting point. Here we use the this one here, that 1 mole sodium is 23 grams, or 23 grams sodium is 1 mole. So you cancel out the gram sodium, and now our target is to go from gram sodium to grams sodium oxide. So now we can, from the balance equation, we can relate the sodium to sodium oxide. So as we see here, the balance equation here, 4 moles of sodium can generate 2 moles sodium oxide. So mole sodium is gone. Now we got mole sodium oxide left. So we're not looking for moles, we're looking for grams. So you have to do one more step using the molar mass of sodium oxide. So 1 mole sodium oxide is 62 grams. So you cancel out, and what is left is grams sodium oxide. That is what we're looking for. So we stop there and we do the math here. 2.3 times 1 times 2 times 62, and then whatever number you get divided by 23, and then whatever number you get divided by 4. So you come up with 3.10 grams sodium oxide. So that means if you start with 2.30 grams of sodium, you can generate 3.10 gram of sodium oxide. Again, those are, we use the coefficient, we use the first we have to balance it, we have to use the coefficients as our bridge or ratio, conversion factor to solve the problem here. This is another question. Is phosphorus burns in oxygen to form tetraphosphorus decoxide. But again, we can't use this unbalanced equation to solve this problem. It has to be balanced first. Again, this is an easy one because we got, yeah, so we got 4, the phosphorus, they are fine. It's just the oxygen. Here we got 10 oxygens, so you just put 5 in front of oxygen. It balances the reaction here. So on both sides, you got the same number of phosphorus and same number of oxygens. So the question is, how many grams of P4O10, that's tetraphosphorus decoxide, the molecular weight is given here, would be produced when 62.0 grams of phosphorus burns. So again, P4, the molar mass of P4 is 123.9, If it is not given there, you can always find it from periodic table. And of course, you got in periodic table, it is like 15 point something. It is molar mass of uh, one mole phosphorus, so you have to multiply by 4. Anyhow, so again, the starting point is 60.0 grams of phosphorus, and we have to convert it to moles, and to do so, we have to use 123.9 gram is 1 mole. 123. And again, the reason we have to convert grams to moles, because the coefficients are moles. It's like 1 mole phosphorus reacts with 5 moles of oxygen to form 1 mole tetraphosphorus decoxide. And so here, because we're looking at how many grams of P4O10, we have to relate that to, it is 1-to-1 ratio, right? And so we can write it here. 1 mole phosphorus generates 1 mole P4O10, and they will cancel out, and you got 1 mole. So your unit at this point is mole P4O10, but we're looking for grams, so we have to use one more step by using the molar mass of that compound. So 1 mole P4O10 is 142 grams, so you cancel out, and so that's gram P4O10. That is what we're looking for. We stop there, and 62 times 1 times 1 times 142, and whatever number you get divided by 123.9, and you come up with 71.1 gram tetraphosphorus decoxide. So that means if you start with 62 grams of phosphorus, when you burn 62.0 grams of phosphorus, you can generate 71.1 gram of tetraphosphorus decoxide. The second part of this question is how many moles of oxygen are needed to burn 7.0 moles of phosphorus. So again, here we compare oxygen and phosphorus, right? So our starting point is 7.0 moles of phosphorus, and so that means you will need 7 times. So when you multiply this by 7, that will be 35. So you can solve that. And 1 mole phosphorus, when the reaction is balanced, so 1 mole phosphorus requires 5 moles of oxygen, and you cancel out the moles phosphorus, and what is left is mole oxygen, and that is it for this second part. It's simpler. We just stop there and do the math here. 7.0 times 5 moles of oxygen, so you come up with 35 moles of oxygen. Now, similar question is silver metal. The molar mass is silver is given 107.84 grams per mole, reacts with concentrated nitric acid. That is the chemical formula for nitric acid, and that is the molar mass 63.0 grams per mole to produce the red-brown gas nitrogen dioxide. So the balance equation is given. Again, we don't have to balance it. It is already balanced there. 1 mole silver reacts with 2 moles of nitric acid to form 1 mole nitrogen dioxide, 1 mole silver nitrate, and 1 mole water. So how many grams of nitric acid are required to use up to completely consume 5.00 grams silver? Okay, now the amount of silver here is given in grams. That is our starting point. That is our starting point. So we have to convert that to moles silver, because remember the reactions are red. as moles. 1 mole silver reacts with 2 moles of nitric acid and so on. So we have the molar mass of silver. That means 107.87 gram of silver is 1 mole silver, so gram silver will cancel out. Now you got 1 mole. That is not what we're looking for, right? We're looking for how many grams of nitric acid. So we have to relate silver to nitric acid. And according to the balance equation, 1 mole silver reacts with 2 moles of nitric acid. So the mole silver will cancel out. Now, the unit at this point is moles nitric acid, but again, grams, we're looking for grams of nitric acid. So we have to use the molar mass of nitric acid to convert moles nitric acid to grams nitric acid. So at this point here, the gram nitric acid, and that is what we're looking for, right? So we stop there. Once the unit is there, then we will just do the math, multiply the top numbers. Okay, 5.00 times 1 times 2 times 63.0, and then divide whatever number you get divided by 107.87, and your unit is grams nitric acid. So you come up with 5.84 grams nitric acid. So what does that mean? So to generate to use up exactly 5.00 grams of silver, you have to use 5.84 grams of nitric acid. The limiting reactants in chemical reactions, sometimes if you don't use the ratios, then one chemical might be used up before the other chemical. So always, if you don't have the same ratio, the same amount of chemicals, the same ratio of the chemicals, one will use up first, and the other will remain in the container as an excess, or it will leave out, so it will remain there. So the reactants are mixed in the exact ratio needed so that each of the reactants is completely used up. One of the reactants is completely used up, and so these are a few possibilities, 2 possibilities, and the sum of the other reactant is left over. So let's look at the terminology here. Every reaction that goes to completion has at least one limiting reactant, or sometimes we call it limiting reagent. So the limiting reactant is the reactant used up first. If you have two chemicals and they react with each other, so the one that is used up first is called the limiting reactant. So the limiting means once it is used up, it limits the reaction. So the reaction cannot proceed anymore. It is done. So a reactant that is not completely used up is said to be in excess, meaning enough is present to use up all the limiting reactant, and some amount remains when the reaction stops. So again, so we just talk about those, and so let's give an analogy here. If the recipe of a sandwich is that you need 2 slices of bread, 3 pieces of the lunch meat, and 1 slice cheese. So that is the recipe of the sandwich. But if you have 6 slices of bread, if you have 12 pieces of lunch meat and 5 slices of cheese, how many sandwiches can you make? How many sandwiches? So the And again, the recipe is 2 slices of bread, 3 pieces of lunch meat, and 1 slice. And so based on the recipe here, in this one you can make 3 sandwiches, right? This one you can make what? How many? If each one requires 3, you can make 4. And this one, if we got enough of the other 2, you can make 5. But again, um, the one, the least, the one that we have, if you just start making your sandwiches, you see you used what, 2, 4, 6 slices of bread, completed the gun. So for each one, you use 3, 6, 9. So 9 of the lunch meats are gone, and 3 slices of cheese are gone. So what is left? So you made 3 sandwiches, but 3 pieces of lunch meat are in excess, and 2 pieces of cheese are in excess. So those are that are left over. Can you make more sandwiches out of those? No, because you're out of bread. So which one is used up first? Bread, slices of bread. So that means once you're out of bread, you cannot make any more sandwiches. So your limiting reactant here is the bread, the slices of bread. Okay. So that is, so you can relate this to the chemical reactions. So for example, here we got 6 green molecule atoms and 12 orange atoms or red atoms. So when each one reacts with so each green reacts with one red, and so you can that means 6 greens and 6 reds are used up. So because we don't have enough greens, not all 12 or the other 6 red will remain in the container in excess. Reaction stops as soon as greens are completely used up. So you cannot make more of those molecules, those compounds anymore. So what is your limiting reactant here? Which one is used up first? It is green one. So green is the limiting reactant here, or limiting reagent. So let's consider the following reaction. 4 moles of iron, 4 moles of iron react with 3 moles of oxygen and form 2 moles of iron trioxide. If 20 atoms of iron 20 atoms of iron are mixed with 20 molecules of oxygen, and the reaction goes to completion, which reactant is the limiting? So the question here is, so we got 20 iron atoms and 20 oxygen molecules. So which one will finish first? Which one will be used up first? So that will be our limiting reagent. So the rule of thumb is that the one that produces the least amount of product is our limiting reagent or limiting reactant. So that's why we have to find out which one will produce, iron or oxygen will produce the least number of the product. In this case, it is iron 3 oxide. So we start with 20 atom, and so according to the balance equation, 4 iron atoms generate 2 units of iron 3 oxide. And so when you do the math here, 20 times 2, that's 40, divided by 4, that's 10. So 20 iron atoms can generate 10 iron trioxide entities, uh, and so let's do the same thing for oxygen. So we got 20 oxygen molecules, and according to the balance equation, 3 oxygen molecules can generate 2 iron trioxide. Now do the math, so you come up with 13 iron trioxide. So which one gives the least amount of product? So that is the 10 is less than 13. So the iron atoms, because they produce the least amount of product. So the iron atoms in this case, in this example, is the limiting reactant. Okay. So once the iron is gone, is used up, you can't produce any more of iron trioxide. It will stop there. So to make more, you have to provide more irons from somewhere. Okay. Uh, the B part of this question is which reactant is in excess. Well, if one is the limiting reactant, the other is in excess. So the oxygen will be in excess because iron. We just found that iron is the limiting reactant here. C, the iron consumes how much oxygen? We can, again, you can see the relationship there. So we got 20 irons. That is what we start with. And according to the balanced equation, 4 irons are consumed per 3 oxygen. So the ratio here is 4 to 3. And that is what we have here. So the iron will cancel out. Now we got there, you do the math here. 20 times 3, that's 60 divided by 4. So you come up with 15 oxygens. So if you start with 20 iron atoms, you can use up 15 oxygen molecules. And so what happens? So 15 are used up. Initially, we had 20 of those. Now 5 oxygen molecules are left over. Okay. And the final question here, part of the question is, how many particles of iron trioxide are formed? Again, to solve this problem, we have to start with the limiting reactant, which is iron. And again, you start with 20 iron atoms. And according to the reaction, 4 iron atoms can form two particles, iron 3 particles. And do the math here, 20 times 2, that's 40 divided by 4, so you come up with 10, 10 particles, iron 3 particles can be formed. So for this one, you have to use the limiting reactant. And that is what we did actually, that for the beginning of the question when we try to find the limiting reactant, which one produces the least amount of product. The following unbalanced equation, again, to solve this problem, we have to balance the equation first. So there is 14 grams of chlorine gas reacted with 0.3 moles hydrogen. Again, the question is which reactant is limiting? Is it hydrogen or chlorine? Those are the reactants. The first thing we do is we have to convert grams of chlorine to moles chlorine, and so that's 14 divided by 69.9. You come up with 0.200 moles of chlorine. And again, because the reactions are read as moles, so the 1 mole hydrogen reacts with 1 mole chlorine and to form 2 moles of HCl. And so if we have 0.2 moles of chlorine and 0.3 moles of hydrogen, so which one will generate the least amount of product? In this case, the product is HCl. So we have to test it. 0.2 moles chlorine, and according to the reaction, 1 mole chlorine generates 2 moles of HCl, and you do the math here. 0.2 moles of chlorine can generate 0.4 moles of HCl. Let's do the same thing for hydrogen. we got 0.3 moles of hydrogen, and according to the balance equation, 1 mole hydrogen here can generate 2 moles HCl. That's what we have here. And do the math here. So the mole hydrogen would cancel out, and you come up with 0.6 moles HCl. Now, what was the rule? The rule is the one that produces the least amount of product is the limiting reagent. So because hydrogen here, chlorine, because chlorine generates generates the least amount of product, 0.4 versus 0.6. So the chlorine is the limiting reactant here. The second part of the question is how many moles of HCl can be formed? So we found it here. So when you try to find which one is the limiting reagent, you're answering that question, or you can just do it again, do it over 0.200 moles of chlorine, and 1 mole chlorine generates 2 moles of HCl. You cancel out, and you come up with that is the same thing. We repeat it here. So that is how many moles, 0.400 moles of HCl can be generated if you start with 14 grams of chlorine, which is equivalent to 0.2 moles of chlorine. So here, another question, stoichiometry. For the reaction of hydrochloric acid and calcium carbonate, the balance equation, so it is balanced. We don't have to worry about balancing it. It is already, so 2 moles of HCl react with 1 mole calcium carbonate, generates 1 mole carbon dioxide. We don't show ones. If you don't see a coefficient, it means it is 1. 1 mole water and 1 mole calcium chloride. So we got three products, 2 reactants, 3 products. If 0.4 mole HCl is reacted with 0.3 moles of calcium carbonate, which reactant is a limiting reactant? Okay, which one is limiting? Which one consumes first? Again, we have here, we don't have to convert grams to moles. It's already given in moles. 0.4 moles HCl. And according to here, we can pick up any product. We got 3 products. You can use carbon dioxide, water, or calcium chloride. Doesn't matter. So 2 moles, if we pick water as our product, we can use that and just compare those coefficients. So 2 HCl will generate 1 mole water, and so you come up with 0.200 moles of water. For calcium carbonate, we got 0.3 moles of calcium carbonate according to the reaction. So in here we use water, so for that you have to use water again. It is 1-to-1 ratio, so 1 mole calcium carbonate can generate 1 mole water, and so you can 0.3 moles calcium carbonate can generate 0.300 moles of water. So again, what was the rule? The one that produces the least amount of product, in this case is HCl, can generate 0.2 moles of water, which is less than 0.3. So that is our limiting reagent. HCl is the limiting reagent. So how many moles of carbon dioxide can be formed? Now we have to use the limiting reagent here, 0.4 moles of HCl, to solve this problem, because that is the chemical that finishes first or used up first. So we start with that 0.400 moles of HCl, and according to the reaction, 2 moles of HCl can generate 2 moles, can generate 1 carbon dioxide. And do the math, cancel out the moles HCl, you come up with 0.200 moles of carbon dioxide. Okay, so that is how we solve the problem here. Another question here: for the following unbalanced equation, sulfuric acid, that is sulfuric acid, reacts with sodium hydroxide, forms water and sodium sulfate salt. Again, here we have to balance it, right? We got two sodiums here, so you can put two in front, and so um, here you put there. So that is how you, of course, number of water. Sodium will be 2, that's 2. And then sulfate, we got one sulfate there. And H2, 2 here, that's 4. So you have to put 2 in front of water. That is how we balance the equation. Once it is balanced, then we can go ahead and solve the problem using the numbers. So 2 grams of sodium hydroxide, again, when it is given in grams, we have to convert it to moles because reactions are read in moles. So 1 mole sulfuric acid reacts with 2 moles of sodium hydroxide and forms 2 moles of water and 1 mole sodium sulfate. The molar masses are given. Sodium hydroxide is 40 grams. 1 mole sodium hydroxide is 40 grams sodium hydroxide. And here it is given in moles. We don't have to do any conversion there. We just take it as moles. But sodium hydroxide has to be converted to 2 moles from grams, 2.2 grams. Again, 2.00 grams sodium hydroxide, 40 grams sodium hydroxide is 1 mole sodium hydroxide, and you come up with 0.0500 moles sodium hydroxide. So 2 grams sodium hydroxide equals to 0.0500 moles of sodium hydroxide. Again, you start with the moles of sulfuric acid here. We're trying to find out which one is consumed first, which one is the limiting reactant? Is it sulfuric acid or sodium hydroxide? So because we got 0.0100 moles of sulfuric acid, and we know the relationship between sulfuric acid and the product, so we're trying to find out which one will produce the least amount of product. And so you come up with 0.02 moles of water product. So that is the sulfuric acid. We do the same thing for sodium hydroxide. It's 0.0500 moles of sodium hydroxide. And according to the balanced equation, 2 moles of sulfuric acid, sodium hydroxide, can generate 2 moles of water. We cancel out moles of sodium hydroxide, and it is 0.100 moles of water. So as you see, because sulfuric acid produces the least amount of product is 0.02 versus 0.1. So that is like 5 times more. That's why sulfuric acid is the limiting reagent here, because it produces the least amount of water, the product. Okay, and how many grams of water, can be formed? Again, to answer this question, we have to use the limiting reactant, which is sulfuric acid. So our initial amount of sulfuric acid is 0.01 moles, and from the chemical reaction balanced equation, 1 mole sulfuric acid generates 2 moles water, and you come up, again, it says grams. So at this point, we have moles water. So you have to use one more step. We have to convert moles water to grams water. You see, that will cancel out. And now grams water, that means we have our targeted unit. And the rest is just math, 0.01. 0.0100 times 2 times 18, and so you come up with 0.36 grams water. So if you start with 0.0100 moles of sulfuric acid, that is what you can generate. That is the amount of water you can generate 0.36 grams. Now, again, most of the time we, if it is moles of the reactant, moles of the product, we don't have to do any conversion. It's just we use the coefficients to solve the problem. Now, sometimes mass of the reactant is given, then we have to convert it to moles of the reactant. And then we can relate moles. We can always relate moles of the reactants or moles of the products. If you have two reactants, you can compare the coefficients, the number of moles. Okay, so if there is mass of reactant, you convert it to moles of reactant. And from moles of reactant, you can relate it to the moles of the product. If you want to convert moles of product to grams of product, you use the molar mass to do so, and so on. Always write the balanced chemical equation. Convert quantities of known substances into moles. If it is given in grams, you divide it by the molar mass, and so you solve it. Always convert it to moles, and use coefficients in balance equation. Again, the chemical equation has to be balanced to calculate the number of moles of the salt quantity, and then convert moles of salt quantity into desired units. So this is another example here. Methanol burns in air according to the equation. So it is balanced here. 2 moles of methanol alcohol reacts with 3 moles of oxygen to form 2 moles of carbon dioxide and 4 moles of water. The question here is if 209 grams of methanol, the molar mass of methanol is given, 1 mole is 32 grams, are used up in the combustion, what mass of water, the molar mass of water is given, is produced. So basically, you got 209 grams of methanol. If you burn it in oxygen, how many grams of water can you generate? What is our given? What is our starting point here? This is the equality. That is equality. That is our starting point. 209 grams of methanol. Okay, so what we have to go, the target, we start with grams of methanol. We have to convert it to moles of methanol using the molar mass of methanol. Then we have to relate it to moles of water using the coefficients, methanol and those two. And then we convert moles of water to grams of water. So there are a few steps there. And so here to convert grams to moles of methanol, we have to use molar mass of methanol, which is given in the parentheses here. To go from moles of methanol to moles of water, we have to use the coefficients. Methanol here, methanol to water. You see, it is two methanols can generate 4 moles of water. And finally, because it says what mass of water, we have to convert moles of water to grams of water. So we have to use molar mass of water. So again, our starting point is 209 grams methanol. Always units, they have to be there, but to kind of be clear, we can use the labels as well. So we start with 209 grams of methanol, and again, we have to convert grams methanol to moles. We have to use the molar mass. So 1 mole methanol is 32 grams. So the reason we put it denominator, we want to get rid of those grams methanol, okay? And then according to the balance equation, we know that 2 moles of methanol, you see methanol is on top here, so you have to use 2 moles methanol according to balance equation here. 2 moles can generate 4 moles water. And are we there yet? No, we're looking for. So far, when you cancel those, your final unit at this point is moles water, but we're looking for grams, so we have to use molar mass of water to convert moles water to grams water. And now you cancel out the units, and so now you got grams water, your last unit, your final unit. And what you just do the math: 209 times 1 times 4 times 18, whatever number you get, divided by 32, whatever number you have, the answer you divide by 2, and that gives you 235 grams water. That is your answer. If you burn 209 grams of methanol, you can generate 235 grams of water. So this is another question here for unbalanced equation. Again, here what we have, this is your starting point. We got 2 irons here, and what we can do is we can put 2 here, and so sulfur became 2 here, so you have to put 2 here. So now you got 2 sulfurs on the right, 2 sulfurs on the left, 2 irons on the left, 2 irons on the right. So what to do? The oxygen, how many oxygens we got now? 2 times 2 is 4, plus 3 here, 7 oxygens, right? 7 oxygens. So how can you make this 7? The only thing you can do is 7 over 2. So to make it, it's like 3.5 basically, 7 over 2 oxygens. But again, as we said at the beginning of the lecture, that because atoms are whole numbers, so you don't have a fraction of like half an atom, or 2/3 of an atom. You can't have that. You have to have a whole number, and that's why we have to multiply the whole thing to just get rid of this 2 here by 2. So you multiply everything by 2. So you come up with this becomes 4. That 2 will cancel out that, so it becomes 7. Here it is 2 and 4. Those are the coefficients. Now we can use those coefficients. We balance the equation. You can solve the problem. So the starting point here, starting with 0.48 moles of iron 2 sulfide and acts as oxygen. So we don't need to find the limiting reagent because we know that we got enough oxygen, but we got 0.48 moles of FeS, iron 2 sulfide. So how many grams of iron 3 oxide can be formed? So again, our starting point is 0.48 moles of iron 2 sulfide, and then we use the equation, the balanced equation, iron, this one here, and Fe. So it is 2 to 4 moles of iron 2 sulfide can generate 2 moles of iron 3 oxides. So you can cancel out. So it's moles of iron 3 oxide, but here how many grams of iron 3 oxide? So we need to use the molar mass of iron 3 oxide that is given here to solve, to convert moles of iron 3 oxide to grams of iron 3 oxide. So here we got grams iron 3 oxide, so that is, we stop there, right? So, and the rest is just math. 0.48 moles is gone, right? Mole iron 3, so it is 0.48 left there. Here is 2, only 2, divided by 4 times 159.6 grams. That's the unit left there. So this unit is gone, for example. So do the math, you come up with 38 grams iron 3 oxide. Now you can do This one here, again, this is similar to the previous questions. They always start with the given, and that is the given 230 grams nitrogen oxide, dioxide, and 46. That's the molar mass of nitrogen NO2. So 46 grams of NO2 is 1 mole NO2, and so you do 3 moles NO2 react with 1 mole water. And 1 mole, we're looking for how many moles. So we're done. We just do the math. 230 times 1 divided by 46 divided by 3. So you come up with 1.67 moles water requires to well, we have to double check the number, so that double check 1.67 moles. And how many milligrams of the same reaction, but a question is slightly different. How many milligrams of NO can be formed from 2.4 10 to 23rd many molecules of NO2? Again, whenever you have particles, you always use you have to use the Avogadro's number. That is the start point. We know that 6.022 10 to 23rd many NO2 is one equivalent to 1 mole NO2. So according to the reaction, 3 moles of NO2 can generate 1 mole NO, but we were looking for milligrams of NO. So far, it is mole NO. We have to 1 mole NO can be 1 mole NO is 30 grams NO, so that is the molar mass, and 1 gram NO is 1,000 milligram NO. So you come up, when you do the math, you see this 10 to 23rd. One is the numerator, the other is denominator. You can cancel out, and then you can multiply 2.4 by 1 times 1 divided by 6.02 divided by 3. Well, before you do that, there's one number, two numbers here. 2.4 times 1 times 1 times 30 times 1,000, and then divided by 6.02 times 3 here, and that is it. So you come up with 1.2 10 to 4th milligram of NO can be generated. Well, that is what we have. It is 1 hour 13 minutes, and please go over these slides again. If you're not comfortable with any of the questions, watch it several times. Make sure you feel comfortable with any of those questions, and also go over your textbook. It contains a lot of practices, so the more practices you solve, the better you learn.